Okay.
I'll turn off my camera and stop talking bandwidth.
No, no worries. Yeah. Okay. Oh, sorry. I was about to. Okay. Hello, everyone. Thank you for joining me for the San Diego 65 session. Today is August 20th, 2024. Uh, if you are new, we're meeting every month, usually kind of the third week or the third Tuesday. I just trying to make it consistent. Sometimes it doesn't work well, but it's usually the third Tuesday of the month. And I always welcome, that's what happened today. Always welcome people to approach me and suggest ideas and present. I think this is a great opportunity for visibility and learning something new and sharing knowledge. So this is what we have today uh, as part of the agenda. Uh, so today we have Guo Ci, and I hope I pronounced your name correctly. We were just only uh, doing IM between uh, ourselves, and so we never had a chance to chat. Uh, so he's our guest speaker for today. We'll be presenting two techniques that are being used to optimize C++ code. The first one is doing binary searches with equal range, with std ranges and the standard library itself without ranges. And the second is customizing the three-way comparison operator, what we call the spaceship operator. Guo Ci is a bioinformatician at the University of Michigan, working in labs doing proteometic, proteomics and genomics research. I actually uh, did some preparation on that some few days back, and I forget how to pronounce these names. Sorry about it. And then we have a couple more things if time permits. So without further ado, I'll stop sharing, and you can start sharing your material. I don't know if you're speaking. I cannot hear you. Gu, are you able to hear us? Oh, I can see him on the call. Yeah. Um, I think you have some audio issues, so we'll wait a few minutes so we can. Your mic is not working. Okay, you can try if you have a different audio. Uh, okay, so he's gonna try a different computer. Anyone is new here, by the way? Okay, I can see him joining from another machine. So
Okay, can
yeah, I can hear you, but there's an echo.
how about
Try now.
okay? Does it work now?
Yeah, yeah, yeah. You can take over. We can hear you.
Okay,
Yeah, we can see the slides.
okay. Thank you. Today I'll be talking about two techniques that I've used in my C++ projects. So the first one would be to customize the three-way comparison operator. Okay. So to start with, we'll have this struct with three data members. So when we default the special operator, the comparison order will be first we compare A, then B, and C. And for the exact rules that, y- sorry, from CP reference, we can get rules when we have base class and array type as subobject. So this struct is 8 bytes. But we can further optimize it by rearranging the data members. Right. For example, if you use if we rearrange it to A, C, and B, then it can be reduced to 8 bytes. Okay, but what will happen when we rearrange the data members? The switch operator will also change accordingly. So we have to be careful when we refactor our code. So one way to fix that is to implement our own spaceship operator. But when we have a user-defined spaceship operator, the defaulted operator equals will be taken away. So we'll as well have to explicitly default the operator equal for this class. Do you think there's a better way to do that? Yeah, we can use std tuple. So you can use the type function to create a tuple, and then we use the spaceship operator to compare them. Okay, next, we consider a case when we have to transform the data member before we do the comparison. So in this example, I've a float that I want to multiply by negative before you compare. So now when we transform the data member, we'll have a R value. So now we cannot use std type because std type will only accept L values. So we can either use the make tuple function or the tuple constructor with CTAP. There are minor differences between CTAP and make tuple. So if we use the constructor std tuple, it will not decay the reference wrapper that we have created using std cref into a real C++ reference. But this difference doesn't matter in this case. So as long as both sides we are consistently using make tuple or the std tuple constructor. Okay. In the previous example, I use a negative multiplying the float by the negative to reverse the comparison. But not all data types will allow you to do that. For example, strings. So the correct way to reverse comparison is just to swap the arguments. Yes. There's still one more possibility that we can consider. Let's say we have a Fourier comparison for a data member, but we do not want to use that. Instead, we want to use something else. Or for example, for floats, the operator spaceship will always return a type of partial ordering. And that's because floats can compare as unordered, and only partial ordering has that value. So, but there's another alternative to compare floats that will give you a strong ordering. So I think it's specified in this standard. So if you want to know that order, that list is what we have when we use this method to compare. So another example would be a case-insensitive string comparison. So by default, it's case-sensitive. But what if we want to use a case-insensitive string comparison? Okay, one possible way is to create a wrapper class that will contain that data member, and then we implement the spatial operator and operator equals for that. But in this case, for every instance where we want to change the default spatial operator, we have to implement this wrapper class. Okay, next. Yeah, we can use a template to deduplicate. So we can use this template whenever we want to change the default spaceship operator. Okay, so for short summary, for this spaceship operator, we can consider changing the comparison order or transform the data member before comparing. We can also reverse comparisons and change the default three-way comparison function for the data member. Any questions before I move on to the next topic?
Can you go back to the part when you discuss the case sensitive versus case insensitive? Yeah. So the next slide, we take a. So you define the strong order float struct where you have. By the way, the reason you need to have the equal is that as far as I recall, when you define your own spaceship, you lose the equal. This is why sometimes you have it equal default, and sometimes you implement that, right?
Yeah, right.
Okay, so you have a strong order on both of them, and then you are using that, or you're using that in the spaceship operator of the struct E5.
Yeah, right, over here.
Got it. Okay. Yeah.
Yeah.
And then you generalize that in the template, which was the next slide.
Yeah, right.
So you have some concepts regarding invocable that
Yeah,
you
right.
would like.
So
Oh, it's a functions.
okay.
You pass functions that would do that for you. Okay.
Or do you want me to explain this part?
Yeah. Go ahead. Yeah.
Okay, sure. Okay, so this custom is a function object, and you construct it with either one of these three-way uh, comparison function. So in this case, it's the strong order.
Mhm.
There's a second optional one, which is for equality comparison, but yeah, that's optional. You can get it from just from the three-way comparison.
Yeah.
So
It's an aggregate that you initialize with the first one. The second one is default to null pointer.
yeah, so this becomes this strong order f is a function object now, and
Mhm.
it takes one argument, which is the data type, right?
Mhm.
So what it returns is this custom type.
Yeah.
So this custom type will have this operator spaceship and the operator equals. So for operator equals, if the function for equality comparison is not provided, then it will use the three-way and compare it to 0. So
Yes.
this comparing to 0 means it is whether it is equal or equivalent. Yeah.
Yeah. Thank you. Yeah. That's really nice.
Okay. Yeah. So those constraints are actually optional, but it should give better error messages if the user doesn't use it correctly. Okay. So some caveats. I think just now you mentioned regarding the operator equals. So let's look at it. Yeah. If we use that example and we look at the operators equal, you'll notice that the operator spaceship for E5 will not use any code in operator equals over here. But if we do not implement this, then this will not compile because operator spaceship for E5 will return a weak ordering, and we'll want to investigate why this is so. So we have to look at how we look into how the difference between the class defaulted operator spaceship and the operator spaceship for stud tuple. So the main difference is for a class defaulted operator spaceship, it will invoke the operator spaceship on each of the data members with the rules that we have shown previously. So, but for operator spaceship of stud tuple, it will use the syn3way function. This syn3way function is a exposition only function defined in the standard. So it is probably implemented in your standard library, but you do not have direct access to it. So this is taken from CPP reference. So this is the implementation for the syn3way exposition function. So at compile time, it will check if your type satisfy this concept three-way comparable with. So if that is satisfied, it will use the operator spaceship. If not, it will try to synthesize that result and return a type of weak ordering. So if you want the details, you can follow the steps over here. So, but this three-way comparable with will require this concept to be satisfied, and this concept requires the operator equals on the type. So we can observe one, I would say, surprising behavior of SYN3-way. So SYN3-way is a private function, so we can't use it directly, but we can use it indirectly. So this will be one way to do it. We can still tie the two arguments, then use the operator spaceship. This will give you the exact behavior as the SYN3-way exposition function. So next, we create a class with one float. We default the operator spaceship, and then we delete the operator's equal. So what happens is that when we do a SYN3-way, it return weak ordering. A type of the return type is weak ordering. But this is surprising because partial ordering can never be converted to weak ordering because it has a unordered value, right? Okay, the next related item that I want to bring up is the compare three-way function object. This is in C++20, so you might not be familiar with it. So this function, I think, is only used by the algorithm lexicographical compare three-way. So it's used as a default comparator if you don't specify any comparator. But in this case, compare three-way will not compile if you do not have that concept three-way comparator with satisfied. And also similar to the SYN3-way, this will never execute any code in the operator equals. It just requires it to function. So quick summary. So for defaulted special operator for class, the operator spaceship will be invoked on each data member. But for stored tuple and some other stored containers, then SYN3 will be used. So if you do not provide that operator equals, it will just give you a weak ordering. So for compare three, it will not compile. So I think that when you, for any class that is involved in this SYN3 comparison, always implement the operator equals. Yeah, any question before I move on to the next? Okay, I'll move on then. Okay, my next topic is on a more generic equal range. Okay, so we have actually we have 4 binary search algorithm. So I think the most commonly used would be lower bound, upper bound, and equal range. So the lower bound will always return the first element that's not less than the given value. The upper bound will return an iterator to a first element greater than a certain value. And equal range will give you a range of element matching a specific key. And I think there's still one more that will only return you a Boolean value. I think that's Boolean search. Okay. I can't remember the exact name. Okay.
I think it was binary search, if I'm not mistaken, if my memory, just the
okay.
binary search function, yeah.
Yeah, it only returns a bool value, no position given. Yeah. So to simplify my explanation, I will use integers and floats as data types. But I think that can be extended to other user-defined types. So for example, if you use com as a comparator function, a less than b can be extended to com ab, and a less than or equal to b can be extended to not com ba. Okay, so here's the problem I have. In a sorted array, I will want to find a range that satisfy the condition that it is in between lower and upper inclusive for all elements in the range. So if lower is equal to upper, we can use equal range. And when upper is low, lower is lower than upper, then we can use the lower bound with upper bound. So in this case, when we do that, we will probably have multiple access to the same elements in the array. So think about it, if the first one will certainly be the same because it will be somewhere in the middle of the sequence. Yes, we can also consider another alternative, which is to use to invoke lower bound or upper bound first. Then we have that iterator and we can shrink the search space for the second call to upper bound or lower bound. But it depends on where the target range is at. If first two is near first, in the first case, then there's not much reduction in search space. And yeah, it's an arbitrary choice between the two alternatives. Okay, so there's a third alternative, which is to make equal range more generic. So the idea is to use equal range with a custom comparator that is derived from the comparator that you use to sort the sequence. Because equal range requires all the target range to be equal to a particular value, we can write a comparator function that treats all those in that interval to be equal. So let me show you with some code. So the whole implementation is only about 30 lines, and let's look at the interface. So the first two arguments will be the iterator pair of that sequence. Then second would the next two would be the values for lower and upper. Then the com is the comparator function that is used for sorting. And then there's a projection which defaults to identity. Yes, so this is the part where we take the sorting comparator and transform it to another comparator that will hand it over to equal range. So this is okay, so we have a ternary operator here. So this condition means that if both arguments, if either one is outside of the interval, then we'll use the sorting comparator to compare. But if both are inside, then they will be considered equal, right? So we return false. Okay, then after that, we will just hand over that new comparator to equal range. So that value can be lower or upper or anything in between. Yeah. Okay, so some benchmarks I did on Quickbench. Yes, so the first one is where we use where we invoke lower bound and upper bound with the same iterator pair. And the second is when we use one to reduce the search space for the second. Yeah. And the third one is this generic equal range method. So we can see that in both three of the scenarios, the generic equal range performs the best, although it's not very much better than the second best alternative. So, and there's also a cache effect. If we increase the number of arrays that we have, then we'll see that the performance get better for the generic equal range. I've also tested it on my machine, a Intel Skylake machine. In addition, I also added the fastmath option, and I varied the architecture option. So one I use Broadwell, and the other one I use the Skylake, which is equal to native, yeah, for my computer. So you can see that the generic equal range performs much better than the second best alternative in both cases. Although it's quite surprising that when I use the Skylake architecture, this second alternative is very much slower. Yeah. Okay, so I'll explain the algorithm for equal range. So the high level overview is to find a position in the result range with binary search, then use lower bound and upper bound to find the range. So we will start off with 3 iterators. So the first one would be, okay, the left will be at the beginning, right at the end, and we have mid somewhere in the midpoint of the sequence. Then we evaluate the value at mid. Now if mid is not in the target subrange, then we can either update left or right. Then we repeat this process until the mid is in the target subrange. Then from there on, we can just use a lower bound or upper bound to find the target subrange. So we can look at this ASCII art to demonstrate the algorithm. Okay, for one, we'll just at step 1. So at the second line, since we evaluated M, we know that L can be shifted to this M, and then M will take the middle. Yeah, and so on until we find that M is in this target subrange. Then after that, we'll use lower bound, apply that on the range from L to M, and upper bound we'll apply on M to R to get the target subrange. So you can look here for the source code of the of equal range. So I realized that all 3 of those compilers implement them in the same way. Okay, so summary. By changing the comparator function to equal range, we can make it more generic. We can replace all usage of pair of lower bound and upper bound, where the lower is lower than upper, and possibly with better performance. Yeah, any questions?
Yeah, thank you. Do you have the benchmark code and the generic one somewhere?
Yes.
You have it. Okay, so you
I
can post it later. People might want to take a look at that.
Yeah, it's actually a hyperlink here. So
Oh,
if you
okay.
get my link to my slides, then you can get it.
Okay, I'll get your slides and I'll post it
Okay.
to others, and they can take a look at that. Thank you so much for the presentation. I'll let others kind of chime in and ask questions. I think there were a few discussions in the chat. So, folks, if you have anything that you would like to ask, please go ahead. So, first of all, did I pronounce your name correctly?
Oh, no. My name is Guo Ci. If that's too hard, you can just call me GC.
Just
Yeah.
okay. Can you? Because I think I did a very poor job introducing you. So can you just introduce yourself again so others know what you're doing and the domain that you are working on?
Oh, okay. So, my name is Guo Ci. I'm working in the University of Michigan. So, I previously worked on uh, usually writing software for scientific research. So, I've worked in a lab doing proteomics research. So this doing research on mass spectrometry. Yeah. Then now I've moved on to a lab doing genomics research. Yeah.
Thank you. You're not in San Diego, obviously, right?
Right, right.
Okay. Thanks for approaching me, and thanks for doing that. I highly appreciate that. Thanks. It's very interesting, and I'm looking forward to see you again in the future.
Yeah, sure, sure. I have more things to say.
Good. Good. Okay. So, folks, we have another couple, not couple, but about 10 minutes. I have a few things that I can share just to have the next 12 minutes. If there are no further questions, uh, so if not, I'll take over, and we can just close with a few couple things that I prepared. So thanks again. Okay, let me share. Okay, so hopefully you can see my slides. So what I wanted to quickly go over today, and usually I find these ideas during discussions with the team and code reviews and so on and so forth. Uh, we have all kinds of new features in C++11, and they change sometimes the semantic of your class, what you can do with your class. And there's a lot of terminology that we need to remember. And I just want to pick one of the terminology and one of the use cases and just discuss that. What happens to your class when you add equal default to your constructor? So you have a class type, and so sometimes you would see class types with empty constructors. Sometimes you'll see classes with an equal default. Uh, Sometimes they are needed, sometimes they are not. But we'll discuss. Let's assume they are needed, and what does it mean to the class? Okay, so this is inspired again by some code reviews, and I looked online to see what other are thinking about that kind of use case. So here's an example. You have two class types, both of them named dog. One would have a private int x, one would have uh, uh, just that, and the second one would have private int x and another public user declared, not defined, but user declared uh, constructor by having the C++11 equal default. So what is the, like, is it, are these two the same? Yes or no? We'll see in a second. So first of all, CPP reference has a lot of details about uh, this type of use cases. I specifically zoomed in to an aggregate type, and a few things about CPP reference. If you able to create an account, you can have another few features that if you as compared to if you just log in as a guest, you can specify a specific standard, and it would show you a view of the specific standard that you're looking at. So this is nice, by the way. So what I would like to zoom in is aggregate types, CPAPAS 20 versus before. So we'll see that things actually changed. It's not happening a lot, but it does happen from time to time, and it's really important to understand what's actually changed. So aggregate types, I really like aggregate types as much as possible, using it as much as possible, as long as it's doable. It's easy to initialize an aggregate from initializer list. So kind of a form of curly braces list initialization that introduced in CPAPAS 11. It's just easy. Std array, for example, is an aggregate. So if you take a look at std array, it's a simple aggregate as if it was just a C array with more additional things, API and so on and so forth. But it's an aggregate. So in order for a type to be an aggregate, there are rules. So an aggregate can be an array type or a class type, struct or union that has, and there is a list. First of all, we cannot have user declared or inherited constructor. And in CPAPAS 20, it was noted as user declared. And there's also no private or protected direct non-static data member. So basically, just to begin with, these two are not aggregate. Even if we just discounted the part of the constructor, they're not aggregate because they have a private int x. So that's one thing. So this is if you just have the diff between CPAPAS 20 and the rest. So what is highlighted is what changed. No user provided, inherited, or explicit constructor. Provided, user provided. So that's until CPAPAS 20. Since CPAPAS 20, user declared. So user provided is like fully implemented, defined constructors. So you could have an aggregate in CPAPAS 17 with a user provided constructor. This is not an aggregate anymore. You can have a user declared or inherited constructors. So even user declared are not going to work. So this is CPAPAS 17. No user provided, inherited or explicit constructors. In CPAPAS 20, no user declared. So what does it mean? The easiest thing that I was thinking to demonstrate that was just showing how it looks like on Goldbolt on Compiler Explorer. So we have a dog class, a horse. So both of them, they have a private members, int x, and since the default access specifier of class is private, int x is also private. The dog has user declared, the class horse doesn't. Both of them are not, as you can see here, they're not aggregate. Swan has a public int x, and cow has a default constructor, but no private. So you can see that dog and horse are not aggregate. Swan is an aggregate. It has a public member, no constructor defined or declared by user at all. Okay. In cow, we have a user declared, but it's still considered in CPAPAS 17, and this is the compiler that I used. It's still considered as an aggregate. If we swap it to 20, just the same exact same code, Swan is still an aggregate, but that's the only one that is an aggregate for this out of these four. Cow in C++ 20 is not an aggregate anymore. Why? Because in 17 I am allowed to have a user defined, no user, sorry, not user declared, not user defined. As you can see here, not user provided. So that still an aggregate. So if you can imagine code that actually using aggregate initialization, and you port it from C++ 17 to 20, that become something that might fail. So the question is why? Like you would see code like the one I'm pointing here, like how, and the question is why? Why do you need? Like you need to ask in code review, like why do you need to declare this constructor? Because it definitely would, if it's not making issues right now, it might make issues in the future. People in 17, people would use it in a specific way. It's aggregate, and it would stop compiling in the future. So be careful with what you place in your class. There are, I think in CPP on C, there were at least one session that we actually went through many months ago regarding what happens when you have a destructor, and what happened if you have a destructor in your base class, how that would impact the derived, and the fact that you are losing the move operator when you have a destructor. So all of that is important. It's the same idea. People would have an empty destructor, and just because people think that if you don't have the destructor, the object would not be destroyed, which obviously that's not the case, because the compiler would provide a destructor. It might be a no-op, but it might do stuff as unwinding the object and just destructing the members in a reverse order. So so that's basically the same idea. Just be careful with what you add. Okay, we have another couple minutes. I'm gonna go over 2-3 slides, or maybe three slides.
Jacob,
Yeah, any questions, Gary?
I just want to mention, if you remove constructors and assignment operators, it also stops being an aggregate.
If you remove, come again. If you remove,
If you remove them, if you say delete
oh,
them,
delete them. Yes,
which
So,
is annoying. If
it's
what you're
annoying.
trying to say is, hey, I have basically a pod, but I don't want to copy it.
Yes. So here's the thing. And again, I memorize these kind of things. That the way I memorize it is, if you write the constructor equal delete, the way I memorize it, it is as if it's a user declared. So then it's for me, it's user declared. It's not defined, but it's the same, on the same level as user declared. This is how I memorize it. So yeah, yeah, thanks for this addition. It's really important. The bottom line is, like, these are not like nice to have, like, oh, I'm gonna sprinkle all kinds of equal default, equal delete. They might change the semantic of your class. So it's super important, and unfortunately, it's like we need to memorize it or test it with the type traits, just like I did. But it's kind of painful to test every single thing. Okay, this is something super simple that I wanted to bring up, but since I've seen that question coming up many times in my career, so take a look at that. We have a function that has a const int x. We have an int y passed to the function, and you cannot assign 10 to x. Oh, that's perfect. So nothing wrong here. It's actually great. But what I'm going to do is jump here, and then we'll go back to what is wrong. So imagine you split that because of specific reason. You split it into a declaration and a definition. So we have a declaration, like prototype, like go prototype, function prototype on line 3, and then you have the definition. So clung tidy, at least clung tidy, maybe other static analyzer would also have such diagnosis. Would say parameter X is const qualified in the function. It's basically a top level const. It has no effect in the declaration. It does have effect in definition. It's actually very important, and I'll explain why it's important in definition, but it has no merit. It's not nothing that is useful in the declaration. Now, so what is happening here? And I have a couple slides that you can read through, but I'll kind of summarize them. So when you are a caller to the function, you have a declaration in front of you, and you have this top level const. I'm not talking about, this is basically kind of pass by value. It's not pass by reference or pass by const reference. This is the different issue, and this is where consts are important. The pass by value, the top level const is insignificant because I know that you're going to make a copy. I really don't care if it's const inside a function or not. I don't have visibility to the function. I don't really care. It's redundant information for me. It's really redundant. There's nothing I can do with that. There's zero information that I can do to reason about anything, right? You're making a copy, and inside the function, it might be const, but I don't care. If I pass it by reference, it is important for me that it's const or non-const, because if it's a non-const, you might change that, and then I need to make sure that if I want to retain the state of what I'm passing, a const versus non-const reference is super important. Now, having the const in the definition makes a lot of sense. Just like every const, it's important. As a reader, you need to reason less, or need to understand or remember less moving parts that might change, might mutate. So cognitive burden on the reader. Hopefully you're also doing SRP. The functions are small and not hundreds of lines, which unfortunately happens a lot. But if it's const, I don't need to remember that this state is going to change and how it's changing throughout the function. I know it's const. So having const parameter is important regardless in the definition, regardless if it's a top level const or const by value or not. It's important because when I read that, I know that this is going to be immutable one, and it's important. So so that's basically kind of, I have this very short topic just to kind of have a closure on this kind of questions. Anyone has any question on that? That's basically the last slide for today.
Yeah, sorry, what's SRP? You had on your last slide?
Single responsibility principle, that's the S of the solid. So solid principles, the 5 principle SRP, which I think is probably, if I need to rate all the 5, I would rate SRP, the single responsibility principle, as the first, like one of the most important. I think the most important for me. So O is the open close principle, and so on and so forth. So there's this solid. They basically provide rough guidelines on, it's a very high level, but it's super important. It's super important. So SRP, single responsibility, is pretty obvious. Class functions, they have single responsibility. It makes everything smaller, and it's easier to test. Open close, You can extend, but not change. It's tested, but you can extend. And then inheritance is a for the L. Let me see if I remember. Inversion. I think you need to depend on abstractions, and not abstraction depends on the details. And D would be, let me think. Can't remember what D is. Who remembers what D stands for in solid? I have a blackout.
That's a dependency inversion, right?
Ah, dependency inversion. Oh, so that's a dependency inversion. So the I would be
Interface segregation.
interface segregation. Yeah, thanks. Yeah. So it's basically, by the way, let me recommend a book, C++ Software Design. I have it on my desk, so this I'm looking at the so make sure that I have the correct title. C++ Software Design, O'Reilly. It's O'Reilly publication. It talks about solid throughout the book, and it's one of the most recent books that were written uh, in modern, like super modern C++, visitor, pointer to implementation, aggregation, inheritance, all of that stuff. And it talks about solid a lot. So it's a great book if you want to grab something which is very modern and recent. I'll highly recommend that one.
What did you say it's called? It's C++ software
C++
design.
software design by Klaus. Klaus himself is a great speaker, by the way. So if you have a chance to, so I attended at least a couple of his in person, couple of his talks in CPPCon. I highly recommend. He's a really good speaker. Okay. Any questions? Okay. Thanks for joining. See you next time. Good rest of your day. Take care.
Thanks, Kobe. Take care.
Take care. Bye.